All right, in this lecture, we're going to cover scientific notation, the general use of scientific notation. And when I say the general use, that means I'm already done talking about conceptual idea of scientific notation, and now we're just going to go into the mathy idea of scientific notation, as well as performing or moving standard notation into scientific notation and vice versa. And then finally, getting in some mathematics using scientific notation and some applications using scientific notation. Now, in my opinion, these are the more entertaining examples that we can do in a math course because there's just a lot of obscure and also absurd examples you can perform using scientific notation. A couple things you'll need to have prior to getting into this section. You need to know everything about integer exponents, including negative exponents and zero exponents, as well as the laws of exponents. Those two things down, let's start getting into this. So the definition goes like this: a number is said to be written in scientific notation if it is written in the form n, that's a capital N, dot, that's a decimal point, and then just a bunch of little numbers after those. So each of those little n's are just digits, like 1, 5, 1, 2, 8, or something like that. So capital N dot little n, little n, little n, little n, little n times 10 to the p. That's a number given in scientific notation, where capital N is a number in the set. That little e right there means an element of. So n is an element of the set 1, 2, 3, all the way up to 9. So capital N is just a number between 1 and 9, including 1 and 9. And the power p is an element of the set of integers. So remember that z means the set of integers. That means it could be 1, 2, 3, 4, 5, 6, 7, so on and so forth, or it could be a negative 1, negative 2, negative 3. It could even be 0. Now, there's a little bit of a lie with this definition. The slight lie here is that the coefficient, or this number out front, the n, the capital N, could be actually a negative 1, a negative 2, a negative 3, all the way down to a negative 9. And notice I didn't include that in my set of numbers. I could include that in here, a plus, minus, and so on and so forth, all the way down to plus or minus 9. The reason why I didn't initially is that usually you use scientific notation in science. And in science, you measure positive values in general. So weights or distances or something like that. And generally, those are not negative. So honestly, when you see scientific notation in the real world, it doesn't have a negative number as its first digit. Okay. Quick examples of things that are written in scientific notation. Things like 7.1801 times 10 to the negative fifth. That's in scientific notation, again, because this first digit is a single digit between 1 and 9. The rest of the digits don't really matter as long as they're to the right-hand side of the decimal place. And then times 10 to an integer value exponent. Another one is negative 3.1 times 10 to the fifth. And again, this is not very common for scientific notation to have a negative number out front, but some math textbooks have them, and so that's why I'm doing this. But in reality, you won't see that in physics or chemistry or biology. You'll see standard or scientific notation all over the place in those courses, but not with negative numbers. Examples of things that are not considered scientific notation. So examples of not scientific notations would be things like this: 17.1801 times 10 to the negative fifth. The issue with this is that we have this 17. That 17 is not a number between 1 and 9, including 1 and 9. Another thing that's not a number written in scientific notation is 0.001818 times 10 to the 11th, let's say. That's not in scientific notation because this first digit is not between 1 and 9. Another example of a number that's not in scientific notation, 1.11 times 10 to the 3.8. Technically, that's not in scientific notation because the power is not an integer. So in all these cases, there's something that kind of ruins our scientific notation. Now, before we begin into working with scientific notation, I want to write down a note, not a theorem, but a note about powers of 10. And I want you to know how to work with powers of 10 without memorizing something about moving decimals left and right in business like that. The thing I want you to know is if you have a power of 10, like 10 to the 8th power, you have to ask yourself, is that a large number or is that a small number? This you have to become intimately aware of. I want you to have an intimate knowledge of what it means to have a positive power here. That's a positive 8th power. That means that you have 10 times 10 times 10, so on and so forth, 8 times. Well, if I keep multiplying 10 by itself a bunch of times, that's a huge number. I'm not really concerned about what the number is. For right now, I'm just concerned about the fact that it's a huge number. So that's the first lesson I want you to take away, is that when I have a positive power here on 10, it makes it a huge number. And on the other hand, if I look at 10 to the negative 5th, well, remember with negative exponents, which is a prerequisite for this lecture, I can rip off the negative, and that 10 and its exponent will hop downstairs. The exponent will become positive. So that's like 1 over 10 times 10 times 10 times 10 times 10. Now let's talk about this. That denominator is huge, right? 10 times 10 times 10. That's like 1 over a large number. For now, I'm just doing it this way because I think this is a conceptual approach here. If you have 1 over a large number like a million, 1 over a million, well, if I said I have 1/1,000,000th of a dollar, would you say that I have a lot of money? Probably not. You'd probably say I have very little money. In fact, pretty much nothing. So this is pretty much a very, very small number. And that's the lesson I want you to take away from negative exponents on 10, is that 10 to a negative exponent tends to be a smaller number. Now let's start talking about what powers of 10 look like. Let's actually take these two examples. 10 to the 8th itself is, like I said, 10 times 10 times 10 times 10 times 10, 8 times, right? So let's do some pattern recognition, since this is what pattern recognition is really what mathematics is all about. 10 times 10, that's 10 times itself twice. That actually turns into 100. Now, I've taken care of, this is actually 2 of the 10s. This is 10 to the second right there. That is not written well, so let me just point an arrow at that and rewrite that as 10 to the second. That's 10 to the second right there. We still have 6 more 10s multiplying up. So let's see, if I multiply that by another 10, that'll become, let's see, 100 times 10 is 1,000, right? And then we still have 10 times so on and so forth all the way down the line. But now we've multiplied up 3 of our 10s. It's 10 to the third. And notice how many zeros we have. 3 zeros. If I multiply the other 10 in there, I'll have, let's see, 1,000 times 10 is 10,000. And I still have a bunch of 10s multiplying here. But we've taken care of 4 of those multiplications. That's 10 to the 4th. And notice there are 4 zeros. Well, pattern recognition tells me that if I want to get to 10 to the 8th, it'll be a 1 with 1, 2, 3, 4, 5, 6, 7, 8 zeros. That is 10 to the 8th. So that is 100 million. Just the commas kind of help us out. So in general, 10 to the positive power, let's say to the positive p power, I'll write a little plus in there to show us that it's positive, is equal to 1 with p zeros. That's one thing you should already kind of know from a prerequisite course. Now let's look at 10 to the negative 5th. Well, that's 1 over 10 to the 5th, like we said, which I wrote as 1 over 10 times 10 times 10 times 10 times 10 times 10. One way you could look at this is like 1/10 times 1/10 times 1/10 times 1/10, right? Keep going on all day, right? And if you take a look at this, the first two that multiply together, which is 1 over 10 squared, is going to be 1 over 100. I still have 3 of those 10s left. 1 over 100, by the way, as a decimal is 0.01. Okay. And now I'm going to go ahead and multiply that by 1/10. So we have 1/100th times 1/10 becomes 1/1000th. And I still have 2 more of those 1/10ths multiplying. But 1/1000th here, I don't know if you can see this, might be off the screen. So let me do this. 1/1000th as a decimal is 0.001. Notice I added another 0. And that is, by the way, 10 to the third in the denominator, or in other words, 10 to the negative third in the numerator. So if I do one more, I'm kind of bored, so I'm not going to really do one more. Maybe I'll just let the cat out of the bag. If this right here is 10 to the negative second, that's 1 over 10 squared, or 1 over 100. Notice that it's basically 1 where the decimal's been shifted to the left 2 times. So it's started as 1, but the decimal's been shifted to the left twice. And here's 10 to the negative third. And that's basically like a 1, but the decimal's been shifted over to the left 1, 2, 3 times. So 10 to the negative fifth would basically be like a 1 with the decimal shifted to the left 1, 2, 3, 4, 5 times. Fill in these little divots here with zeros. So there we have it. That's the way you can kind of deal with powers with negative exponents. And so the idea is that 10 to a negative power is going to be 1, but there'll be, how do I say this? With p minus 1 zeros before it. So in this case we had 10 to the negative fifth, so we'll have 4 zeros before it, and then you'll have a decimal place. If it was 10 to the negative 18th, you would have 17 zeros before it in a decimal place. All right, so now that we've kind of talked about that, and by the way, I don't memorize that. I don't memorize how many places I move over. I've done it enough that it just kind of is there. So I guess I have memorized. It's like muscle memory in a way. Let's go ahead and approach writing a number in standard notation. So I'm going to give you a couple numbers that are written in scientific notation, and we'll change them to standard notation. And I'll just make these up. So let's do 3.17, and I'll say times 10 to the 14th power. Now what I ask myself, I don't memorize things, I just ask myself, is that a large number or a small number, 10 to the 14th? Now we just talked about in the previous page here that 10 to a positive power is pretty large. So 10 to the 14th, that's a large number. So that's definitely going to grow this 3.17 to a very large number. It's going to be like 317,000 or 317 million or 3,170,000, something like that, some huge number. So when you know that, you immediately copy the number 317. You indicate where the decimal place was. It was right here. And then you move that over 14 spots, right? You're growing it by a power of 10. So every time you grow by a single power of 10, it moves it over once. You're growing by 14 powers of 10, so you're going to move it over 14 times. But this tells me that, because a lot of students memorize, well, let's see, if it's positive, I move it to the right. If it's negative, I move it to the left. That tends to fail a lot of students. So instead, you should just think, 10 to the 14th, is that a large number? Heck yeah. So obviously that 317 is going to turn into a huge number. That'll give you a good numeric way to approach the problem. So you have a quantitative approach. Anyway, let's move it over 14 spots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. My handwriting got horrible at the end. Sorry about that. But that's where our new decimal is going to be. Let me fill in these spots in between these divots with zeros. If you hear a dog barking, I live out in the country. All right. And now, just for us to really understand what this number is, and remember in the conceptual lecture I told you the reason why we like scientific notation is because, one, it's much easier to look at the number. Like this scientific notation, much easier for me to look at than this number with all these zeros in it. The other reason why we really like scientific notation is for computational purposes. But let's go ahead and fill in every 3 spaces with a comma so we can at least get a general idea of the size of this number. And I'll rewrite it without all those divots. So it's 3,170, comma. Let's see, we have, did I fill in these zeros correctly or did I miss a zero somewhere? 1, 2, 3, 1, 2, 3, 1, 2, oops. I did miss a zero. See, that's a problem here. So let me erase this and start over. So I have 0, 0, 0, comma, and another 3 zeros. It's the US notation here. And another 3 zeros. So we have this 3, this group of 3. We have this group of 3 next, so let's go ahead and do that. And now we're left with 317. And to interpret this, let's see, these are the thousands, these are the millions, the billions, this is 317 trillion. So there we go. We know what that is. Now that could stand for a lot of things. It could be the number of grains of sand on this planet or something like that. By the way, scientific notation is where we really get an idea of the fact that we as human beings really suck at understanding large numbers. We have a hard time interpreting large numbers. We'll play with that concept in a moment. Let's do another example. Let's say I have a number like 9.01 times 10 to the negative 5th. In this case, I need to know, is this 10 to the negative 5th going to shrink this number or grow this number? Well, 10 to the negative 5th, as we said in the previous page, when you have a negative number on your, or negative exponent on your power of 10, or on your 10, sorry, that's a very small number. 10 to the negative 5th is a very small number. So this, I'll just write small below it, which means that it's going to shrink that number 9. Which does not mean we're going to go 901,000, because that's a large number. Instead, we'll write 901 back here, and I'm going to throw some zeros in front of it. Now the old decimal place, maybe I'll do this in blue instead, was right here. I'm going to move that over 5 units, and I know it's got to go to the left because the fact is this number is going to shrink. So 1, 2, 3, 4, 5 units. So that's where my new decimal place is. And I'll fill in these spots, these divots, with zeros. So this number is the same as 0.0000901. And by the way, I have a habit of writing a 0 before my decimal place. You don't have to. I just have a habit of doing that. There you go. So you now have some experience where you've seen some examples of writing a number given to you in scientific notation as a number in standard notation. Now let's go the other way. Let's suppose that I give you a number in standard notation and I want you to write it in scientific. So if you look at both of these, one's a large number, one's a small number. Now if I want to write this large number in scientific notation, remember it always starts, you basically start reading from left to right and you say, okay, which is the first non-zero digit? Well, 2. In other words, just grab the important information, 2.88. I've decided to write it as 2.88 because the fact is, the number, to write a number in scientific notation, the first number has to be a number between 1 and 9, and it can only be a single digit. So you can only steal the very first digit and then write a period or decimal point, and then follow it up by any pertinent numbers. So 8 and 8, and since the rest are zeros, I don't bother copying the rest. And then I write times, I know to write it in scientific notation it'll be times 10 to a power. So now, again, I ask myself, well, geez, I need a power of 10 here. Is it going to be positive? Is it going to be negative? The way I tend to have always done this since I was a student is I'd look at this 2.88, actually. Say, well, that's basically 2. Well, actually, it's basically 3, but whatever. I want to grow this number back to this huge number. And the only way that I'm going to grow this small number to become this huge number is to multiply it by a very large. I want this to be a large number. Well, for it to be a large number, it has to have a positive exponent. I already know that. To become a large number, it has to be a positive exponent. Aha! There you go. There you have it. So that's actually how I've always done this. I just kind of look at it and go, listen, I need that to be a large number, so it has to be a positive exponent. Let's figure out what the value of the exponent is. Well, here's where I placed the decimal place. So that was 1, 2, 3, 4, 5, 6 spots that I had moved it. So this will be a positive 6. So it's 2.88 times 10 to the positive 6. Along the same lines, we could do the same argument down here. I again read from left to right until I get to the first non-zero digit, which would be that 1. And then I have to put a decimal place and then follow it up with everything else that's pertinent that until I start getting a bunch of zeros after it. So this is actually that 1, 2, 3, it's 1, 2, 3, and then there's actually an infinite number of zeros behind it. But I don't bother writing those because I don't have all my life to write zeros. And then we want to write this as times 10 to a power. But remember, we now have a number that says 1.23. I need to shrink that back down to this really small number. So I need this power of 10 to be very small. And that means I need it to be negative. So let's see. Here's where I have the decimal place in my 1.23. I'm going to see how many spots I moved it. 1, 2, 3, 4, 5, 6, 7. So this will be negative 7th power. So 1.23 times 10 to the negative 7th. So you have to always make sure that your lead number here is always a number between 1 and 9, including 1 or 9. And then that if you're going to grow this number to be large, it's a positive exponent. If you're going to shrink it, it's a negative exponent. Now let's go ahead and play around with some mathematics involving scientific notation. Now this is an introductory example. Actually, it's pretty much typical of all examples when you're dealing with mathematics and scientific notation. You generally just do multiplication and division with them. But this will lead us into a very nice application. I'll just make one up. I'll try to use real data though. But before we can do a real application, let's go ahead and start with this to get used to the mathematics. Now one thing I need to note here, I need you to recall the commutative property of multiplication, which means I need you to recall the fact that multiplication can occur in any order you want. So I'm going to rearrange this multiplication to say 8.8 times 1.101 times 10 to the 14th times 10 to the negative 3rd, all over 2.31 times 10 to the 21st. Now, I'm just replacing these x notation with parentheses. It all means the same thing. They all mean multiplication. And I'm going to take care of the powers of 10 first. So upstairs I have 8.8 times 1.101. 10 to the 14th times 10 to the negative 3rd is going to be 10 to the 11th. Notice that I again exercised my right to combine those two instead of moving the 10 to the negative 3rd downstairs. And now notice I have a 10 to the 11th upstairs and a 10 to the 21st downstairs. And recall that property, when if it was an x to 11th upstairs and an x to the 21st downstairs, I would say who wins and by how much? Well, the bottom would win by 10, right? Same thing here. The bottom of this will win by 10. So I have 8.8 times 1.101 divided by 2.31 times 10 to the 10th, because the bottom won by a power of 10. At this point, I'm going to go ahead and rewrite this just one last time before I do the simple arithmetic. I'm going to write the power of 10 off to the side as times 10 to the negative 10th. Notice what I've done. I've added a negative to the exponent, so I flipped it upstairs. If you don't believe me, rip the negative off this and notice it'll fall back downstairs. So this is part of that prerequisite knowledge of knowing that a negative exponent, ripping it off will flip its position, placing one on will flip its position. Now at this point I'm going to go ahead and just do the multiplication here of 8.8 times 1.101, and then I'm going to divide that by 2.31. And I get some messy number. Now, I'll let you know there's a little trick to scientific notation, especially when you get into chemistry and biology and stuff like that. They generally think, and it's actually kind of true, that the decimal place you're going to round to is determined by the number of significant figures you have. Now, this is not a lecture on significant figures, but the fact is, you look at your original piece of information here. So let's just look at this 8.8. They've given us two pieces of information. This 1.101, they've given me four pieces of information there, right? A 1, a 1, a 0, and a 1. And down here, they've given me three pieces of information. The one that determines how many pieces of information my answer is going to contain is the weakest one. So essentially, I want my answer to have just two pieces of information. So I'm going to round this to be 4.2. In other words, I'm not going to do 4.19 or 4.194. I'm just going to say, listen, because somebody initially handed me something that's very weak, 8.8 is much weaker than 1.101 because it's not as much information there, then I just have to round to that weakest decimal place. There you have it. So this is going to be 4.2 times 10 to the negative 10th. That's how that mathematics works. Now, something that you should know is that that the whole conversation I just had about the significant figures, it's not about decimal places, it's about the number of significant figures. So I'm again, this is not part of this lecture, and I might dedicate a lecture to it in the future. Generally, a problem should tell you what decimal place to round to, or your instructor should tell you what to round to at this point. But if you are interested in learning more about significant figures, just leave a message on the video here down below, and I will go ahead and make a video concerning significant figures and how you can figure out how to round your answers properly. Now let's do an application. So the fun stuff. So let's start with just an example. I'm just searching, today's October 22nd, 2011, so likely is not the date you're watching this, maybe a year after this or something like that. But currently our U.S. national debt is estimated, now this is estimated to be 14, let's see, what is that, thousands, millions, billion, 14 trillion, 14,947,804,581,905.02. Now, obviously, this is ridiculously inaccurate. But you can use maybe a couple or three of the digits to maintain a little accuracy. So let's say that the national debt is actually $14,900,000,000,000. So the first thing I'm going to ask you to do is let's write this in scientific notation. So in scientific notation, because obviously that number is very unwieldy. So in scientific notation, this is, well, let's see, reading from left to right, I'm going to copy the 1 and then put a decimal point 49. And again, I didn't take the entire number that website gave, because the fact is that website's wrong. It's just a guesstimate. And we're rounding it down. And the reason why I'm rounding down, one, is because it's actually proper for this situation. And two, I don't want to overestimate and do some sensationalism. I'm still going to do sensationalism here, but I'm going to do it with more realism. Okay, so 1.49 times 10, and let's see, I need to grow this number, 1.49, into this huge number. So this has to be a large number. So the power on 10 must be positive. And let's see how many decimal places I would have moved over here. So here's the point between the 4 and the 1. I move it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 10 to the positive 13th power. And let me just double check that. 9, yeah, 12, 13. Okay, so this is 1.49 times 10 to the 13th. Now here's the problem with our brains. As human beings, we are all somewhat innumerate. which means that's like the mathematical or the quantitative equivalent of illiterate. We have a very difficult time with large and small numbers. Not very many people, in fact, hardly anybody, can actually imagine what 14 trillion or 15 trillion looks like. So let's try to fathom this. And I'm going to do this in two different ways because I want two examples for applications so that we can kind of really get this. So I'm going to keep this page and then I'm going to move on. It'll seem like I'm moving on to a totally different example, but I'll come back to this, I promise. So here's the example. The average width of a human hair is 0.0039 inches. That's very average. I mean, there's a range, but that's the average. And the average distance to the moon, because that also fluctuates, is about 39,000 miles. So we're going to convert both to scientific notation. The first one, which is a smaller number, remember, read from left to right. The first non-zero number is a 3, then put a decimal point in a 9 times 10. And remember, we want to shrink this number 3.9 down to a very small number, so it'll be a negative exponent. And just count up how many decimal places you would have moved. If you place that decimal place between the 3 and 9, you would have moved that 1, 2, 3 over. So this is to the negative third power, and this is in inches. Got to put this in for this example. The average distance to the moon is 2.39 times 10, and because I want to grow this number, it'll be a positive power. And again, decimal places between the 2 and the 3, 1, 2, 3, 4, 5. Miles. Now, I want to know if I stacked human hairs on top of one another, not end to end, but side to side, using their widths, how many human hairs would it take for me to reach the moon? So let's first say if I wanted to know how many people I need to stack to reach the moon, I would have a distance for a single person and then see how many times that divides into the distance to the moon. So we're really doing a division problem here. We have 2.39 times 10 to the 5th miles. And we're seeing how many times a hair will go into that. 3.9 times 10 to the negative third. How many times? And by the way, these are in different units. So I either have to convert inches to miles or miles to inches, one or the other. But I have to cancel out units here. So let's first start by canceling units. I'm going to change the word miles to inches. So remember to do that. Actually, I'm not going to write the equal sign. I'm going to go ahead and just start doing it here. I need to multiply this by a fraction that gets rid of the word miles and introduces an intermediate step called feet. Well, I happen to know there's 5,280 feet per 1 mile. And if you look at this, 5,280 feet is the same as 1 mile. So really, I'm just multiplying by a fraction that's equal to 1. This is called unit or dimensional analysis or unit conversion. When we do this, the word miles will cancel, and now our numerator is in feet. But I don't want the numerator in feet. I want the numerator in inches. So I'm going to do one more conversion here. I want to rip out the word feet and introduce the word inches. I know that there are 12 inches per 1 foot. So these two lengths, the numerator and the denominator, are the same. So this fraction is just 1. Okay, because the length on top is the same as the length on the bottom, so I'm really not doing anything but multiplying by 1. And you see the words feet will cancel. And by design, actually, this word inches will cancel with this word inches. So this will be a unitless number, but this number will tell me how many times a human hair will go into the moon, or how many human hairs I have to stack up. So let's do this multiplication here. And remember, you can change the order of a multiplication. So this is going to be 2.39. I'm using the commutative property of multiplication here. Times 5,280 times 12 times 10 to the 5th. And I'm going to divide that by 3.9 times 10 to the negative third. Now I'll need more paper for this, so what I'm going to do is copy this and move it to another piece of paper. So at this point, I'm just going to go ahead and rip the negative off that 10 to the negative 3. So when I rip the negative off the exponent, that'll hop upstairs. So this will be 2.39 times 5280 times 12 times 10 to the 5th times 10 to the 3rd. It's the positive third now because I ripped the negative off and it hopped upstairs. All divided by 3.9. And of course, really taking my time with this, 2.39 times 5280 times 12 times 10 to the 8th over 3.9. At this point, I'm going to go ahead and just do this multiplication upstairs. So this is 2.39 times 5280 times 12. And then downstairs, I'm going to divide that by 3.9. And I get this messy number, but I'll write it anyway. This is, let's see, equal to, and actually I'm going to say roughly equal to, because I'm not going to keep all these digits. I'm only going to keep probably the first two. So I'll say 39,000 times 10 to the 8th. I only kept the first two digits because, well, one, maybe the problem, maybe I'm just really concerned about a rough estimation. So really 38,000 is not that important to me. 39,000, just rounding up, would be absolutely fine. It also, I'm doing that because the fact is, well, no, maybe I'll do it to three places because this 2.39 is the worst. Actually, we have, well, no, never mind. 3.9 here. Yeah. So notice there's two digits of accuracy there, so I'm only going to keep two digits of accuracy in my final answer. All right. That being said, is this answer given in scientific notation? And the answer is no. The answer is not, because I need a 3-point something. So what you do at this point is you write that times 10 to the 8th off to the right-hand side. Remember that it's there, though. And I'm going to rewrite 39,000 in scientific notation. That's 3.9 times 10 to the, let's see, 1, 2, 3, 4, times 10 to the 4th. This is how you do it. If you do some computation and then in the end you find out that your answer is not in scientific notation and you want your answer in scientific notation, this is how you do it. So I convert that 39,000 to scientific notation, then I have 10 to the 4th times 10 to the 8th, which is 10 to the 12th. So this 3.9 times 10 to the 12th. That's how many human hairs we'd have to stack on edge to reach the moon. Now, to give you an idea, because people look at that and they go, man, that's impossible. You can't stack that many hairs. Really? Because if you stack that many dollar bills up, that wouldn't even be the national debt. Remember, the national debt is 1.49 times 10 to the 13th. That's a larger power than our 10 to the 12th here. So this is fewer human hairs. We'd need fewer human hairs than we have in national debt to reach the moon. Okay, that's why I was keeping that last example. So this is a cool way. You could do this all day long. Just look up interesting little facts. How much blood does a human body generally carry and how many humans are currently on the earth? And now you can find out how much blood is actually on the earth currently, and then you could see what size of a cube will that fit into. You'll be surprised it's not that large. There's just these fantastically interesting numbers that we don't realize anything about. By the way, before I leave, I'm just going to ask you a question. I'm not going to give you the answer. I'm just going to ask you it. How many, maybe I should say how long, is 1,000 seconds? And then, how long is about 1,000,000 seconds? Now, the difference between the two might be somewhat surprising, or maybe not. But what will be surprising is how much is 1,000,000,000 seconds? This should give you an idea, because think of a millionaire. When you do this problem and you find out how long 1,000,000 seconds is, just think of earning $1 every second, how long it would take you to become a millionaire. And then think about Bill Gates, who is beyond a billionaire. And, I By the way, I wrote a billion incorrectly. Sorry about that. Anyway, think about Bill Gates, who's beyond a billionaire, and how many seconds it would take if you earned $1 a second to become a billionaire. How many days or weeks or months or even possibly years that is. Very interesting.